Log on, tune in, find out. Another good idea from Cambridge.
Well, yeah, it's a beautiful Friday afternoon. Sorry you all have to be here.
Here is bad news. Somebody's made off with the 5-minute sign.
I'm sure this is on.
Bill?
Check what you have in the pocket. If there's a red light, it's on.
There's no little room. Can I move the switch?
Try it.
Now is it on?
The other thing is we used to have these nice cards so that I could stop you,
Yeah.
but they've disappeared.
I don't think it's that long, but
Okay,
if it
well.
gets long, just say something.
Yes, sir. Oh, look.
I didn't my roommates to have tonight. I'm not used to it.
Okay, this is joint work with my doctoral student, Victoria Palma de Ayala, and it should really be titled Sequential Monitoring of Conditional Randomization Tests. And I'm going to talk a little bit of background on randomization tests, which are kind of rare and unpopular, and then I'm going to talk about Monte Carlo methods for computing them, and then I'm going to extend this to sequential monitoring of randomization tests. So 1 and 2 I talked about at the MODA last year, and 3 is the main thing that is the main extension. Now randomization tests, the way I'm going to describe them, are somewhat controversial. I don't know why, but a lot of people seem not to like them. Everyone knows that clinical trials don't follow a population model with random sampling. So in fact, the only random mechanism in a clinical trial is the randomization itself. Several people at the FDA do require a confirmatory analysis using a randomization-based inference that is based on the actual randomization procedure that was used in the clinical trial. They call this at the FDA a re-randomization test. I'm going to call it a randomization test, although I don't consider it the same thing as a permutation test. And sometimes people use them in permutation tests and randomization tests interchangeably. But these analyses are usually done using Monte Carlo simulation, where you regenerate the randomization procedure that you used a certain number of times, and you see how many extreme results you get, and you calculate a p-value based on that. This is the way you do it for an unconditional test, and that in some cases may be desirable. But some people like conditional tests, and I'm going to talk about a particular type of conditional test that arises from conditioning on the random sample sizes, which are ancillary statistics in most clinical trials, unless you're using response adaptive randomization, which I'm not going to be dealing with. Now, if you were going to do a conditional randomization test as a confirmatory analysis or as a secondary analysis, but you use some kind of sequential monitoring in the trial, it's not entirely clear how to do that. And in fact, it would be kind of challenging, and that's another topic I'm going to discuss. This question kind of arose from something that Marvin Zelen said at a JSM a couple of years ago, when he asked, how do you actually generate from the conditional distribution? I mean, it's clear how you generate unconditionally these randomization sequences, but how do you do it conditionally? So we're going to show you how to do that. So the typical clinical trial design, we have n subjects randomized, and we have 2 groups, n1 and n minus n1. And we get the data due to group A and the data due to group D, and B, and we're interested in observing some difference and testing a hypothesis that groups A and B are not different. And so this is a very simple hypothesis, and if they're equivalent, then we say the data is due to just one group rather than separate groups. And in the randomization model, any observed difference would be entirely due to the randomization itself under the null hypothesis. So the p-value of the randomization test would depend on the particular randomization procedure used, and I'm going to call that T1 through Tn. So this is a randomization sequence, T1 through Tn, which are usually just ones or zeros for treatment A or treatment B. Now you could just flip a fair coin, in which case they're all equiprobable, or you could use some blocking scheme, or you could use something more sophisticated like the bias coin design and its generalizations and extensions. The example I'm going to use, although this methodology applies to any kind of restricted randomization, is the Efron's bias coin design. And just to remind you, Efron's bias coin design, we take a look at the observed differences in the treatments, and we skew the probabilities if A's doing, if you've assigned more patients to A, then you would assign a patient to treatment B with a higher probability, and vice versa. So this P is the bias of the coin. Efron suggested the value 2/3 in his original paper, although there's not any theoretical justification for that. So now, I guess the controversial part is that the p-value of randomization tests depends on the type of reference set used. And here we have omega u, which is the unconditional set with cardinality 2 to the n. And then if we wanted to condition on the numbers assigned to A and B, which are random variables but are ancillary, then we would have n choose n1, where n1 is the final number assigned to treatment 1. And then we just have some treatment effect metric, and we calculate that for every possible sequence. And then we add up the probabilities of those particular sequences. So it is different from a permutation test. The permutation people would say, well, I can take any data set, whether it's randomized or not. I can condition on the sufficient statistics, assume that the data are exchangeable, and then I can permute everything in an equiprobable way. I'm actually incorporating the randomization design into the analysis. So the Bayesians don't like that, the permutation people don't like that, and the modelers always come to me and say, well, my p-value is the same as yours, so why are you doing what you're doing? So Rosemary's the only one that understands me. So it's a lot of work to actually incorporate the randomization procedure into the design, and maybe there's not a lot of payoff, but it is fun. It creates some very nice theoretical problems. So just as an example, if we use the bias coin design with p equals 3/2, we observe some responses, and I'm just going to use a Wilcoxon rank test on these for treatments 1, 0, 0, 1, 0. And if you calculate that, the observed statistic is 2. And then if you use you can see either the conditional or the unconditional reference set. For the conditional reference set, you would only have 5 choose 2 sequences that satisfy n1 equals 2. And then you'd obtain the randomization distribution by computing all possible inner products using that statistic on the reference set. So that's the unconditional reference set, and then we've got the conditional reference set. And I'm just using, as I said, the Wilcoxon test on this data. So if you actually calculate the probabilities of each one of these sequences, you get these things here, which are polynomials of p and q and 0.5. So obviously these are not equiprobable, and so if you were actually to do a Monte Carlo generation of these things, you would want to take into account the probabilities. So there are a number of computational techniques for this, and I'll show you a new one. So you could do an exact test, but that gets pretty complicated pretty quickly, particularly for the sample sizes of modern clinical trials. In some cases, the randomization test actually has an asymptotically normal limit. Under Efron's bias coin design, you don't, because it's actually a Markov chain that has a discrete steady state limit. So you don't get a normal approximation. So it's not entirely clear what to do here. So here's the conditional test comparing two groups. So we've got this unconditional reference set, and then we've got the conditional reference set where the sequences are satisfy that condition. So if we were just doing a randomization test from the unconditional reference set, it's very easy. We just use the randomization rule, which in this case is the bias coin randomization, to generate these sequences. And then how many sample sizes, what would be the sample size you would actually need to get a reasonable approximation to the p-value? This, you can show that this would be a negative binomial with the probability that n1 equals little n1 and the conditional sample size. And you can compute this exactly under the bias coin design. It's not particularly easy. And if you were to sample from the unconditional reference set and used the sample size of the Monte Carlo sample size of 2,500 to actually, and then you pull out all the ones that have exactly n1 equals little n1 sequences, you would have to, in order to get these 2,500 sequences that satisfy the condition, you would have to have something like, some astronomical number of sequences generated from the unconditional reference set to pull out the 2,500, if 2,500 is sufficient. So you can't do it that way, basically. So the idea now is, what if we could sample directly from the conditional reference set rather than sampling from the unconditional reference set and pulling out the samples that satisfy the condition? How about generating sampling directly from the unconditional, from the conditional reference set? So that would require adjusting the randomization procedure to generate sequences directly from the conditional reference set instead of from the unconditional reference set. And you can think of, if you were just flipping a coin, how would you generate sequences from the unconditional reference set? Well, you could have an urn. Suppose you observed 20 A's and 30 B's. You could have an urn with 20 A balls and 30 B balls in the urn and just pull out one by one, right? And each one would be equiprobable. Well, in this case, for the bias coin design, they're not equiprobable. They're very complicated. And so you'd have to actually derive that distribution. So here's the formula. This is for general restricted randomization procedures that you can come up with the conditional. You can generate from the conditional reference set using this PJ, and that's going to be a function of the unconditional randomization procedure times some messy conditional probabilities. So these are conditional probabilities of the n1s. So you need to find these first, and that really is not an easy problem. That's a combinatoric problem, and we were able to do that. And I won't show you the formulas because they're really long and messy. So here's the procedure. You use this PJ plus 1 now instead of VJ plus 1 to sample directly from the conditional reference set. And then you evaluate the statistic for each sequence. Use the sample proportion p hat as the estimator of the conditional p-value. And then you can figure out the required sample size in a number of ways. You could perhaps bound the MSE of p hat, which would, according to some epsilon bound, and if it's 0.0001, then you'd have 2,500 sequences. That's probably not, 0.001 is not a really good, very tight bound on the MSE of a p-value, which is small anyway. So you could do something for higher precision. You could just take the probability that p hat minus pc is less than some percentage of pc and make that a high probability. And for that one, you get 16,000. So you'd need 16,000 sequences. So basically, we've reduced the problem from 10 to the 12th down to a few thousand, generating a few thousand sequences. So how would we do this in a sequential monitoring approach? So suppose we want an alpha level test, and we're going to have a number of interim inspections. So I have L-1 interim inspections of the data. And I'm going to use a type 1 error spending function, the Lambda-Metz procedure, and all that does is it's a function that maps 0, 1 to 0 alpha. And typically, you would calculate an information fraction at each inspection to determine the proportion of data that's been examined so far, or proportion of the information that's been examined so far. So a typical sequential monitoring plan, typically you need to find these critical values that gives you an alpha star T1 at the first time period, and then you find the joint another critical value so that the joint distribution of these test statistics have alpha 2 minus alpha 1, and so on, and so on, and so on. So if you have a randomization test now, you're conditioning on the observed number of patients on treatment 1 at each of the interim inspections. And so the first one's conditioned on N1 of R1 is little n11, so that's the observed number of patients on treatment 1 at the first interim inspection, and then the second one's conditioned on the n11 and then the observed number of patients in the second inspection, and et cetera, et cetera. And you can show that this is equivalent to this formulation here, where you now have these intersections that n1 is equal to little n1. And now we can actually do something with this because we can find the exact distribution of these sequentially computed test statistics conditional on these conditions. So at each look, I'm going to sample sequences in the way that I've already done from the conditional reference set that satisfy this intersection condition. I'm going to retain those that satisfy the intersection of the test statistics less than or equal to the critical value. And I'm going to evaluate the current stage test for each of the retained sequences. And then my resulting value will be a Monte Carlo approximation of the required distribution. So the main problem is sampling sequences that satisfy this condition. So this is just a generalization of the previous result. And we were able to compute that exactly using combinatorial methods. So now the other thing you need in a sequential monitoring is the proportion of information, or we can say the proportion of the variance that has been expended by that by the time of that interim inspection. So we don't have a population model here, so the concept of information is not the same as we would have in a population model. We still have variances, which is really what we're interested in. So we can calculate the variance, but now the variance is calculated with respect to the randomization procedure, and in particular, it's calculated conditional on the number of patients on treatment A. So this is the form of the variance of the test statistic at the interim inspection RL divided by the variance of the test statistic computed at the end of the clinical trial. So we need to calculate that variance. So these are conditional variances of randomization procedures conditioned on interim inspection, numbers of patients on treatment 1 at interim inspections, and that is a mess. It's a horrible variance covariance matrix, but we were able to get the result. So I want to go just, let's see, how much, did you raise a, you haven't raised anything yet. You must be doing pretty well. Oh, okay. So I have 3 minutes. I have 3 minutes basically. So, okay. So here's a little conundrum. So, so when we calculate one of these test statistics, this is for the linear rank test. So you have an inner product of these of the treatment assignments and the some kind of ranks. So these are ranks, and they're considered deterministic now under the randomization model. So we can calculate these variance covariance matrices, but at the time that and we can calculate this at the interim inspection because that's the observed data, but what do we do at the end? We don't have the data from the end, so we've got to do something. So we tried various things. We tried to simulate the data under a population model, which is kind of antithetical to the whole point of this. We did a resampling procedure, so we kind of, well, it's not really a bootstrap, we just resampled the data. And so we got an approximation at the end, and since I have 1 minute left let me just show you that without telling you what any of these things are, except that this red dot and this little dot means that if you actually resample the data, it's right on top of the true value. So that was a very good method for approximating. And in fact, we did some time trends and things like that, and we didn't see really any difference. So that seems to be a reasonable way to extrapolate data to the end of the trial so that you can calculate the information fraction. So under efference bias coin design, the conditional randomization test is not asymptotically normal, and therefore we want to generate the sequences directly from the conditional reference set, which should provide a reasonable method of approximating the randomization p-value. So this really answers the question posed by Zellen: how does one compute conditional randomization tests? If you can calculate these things, let me go back, and these horrible here, if you can calculate these horrible conditional probabilities for the randomization sequence, then you can do this. And we did it for reference bias coin design. I imagine you can do it for the generalized bias coin designs. Haven't done it yet. So this is something that, to my knowledge, no one's ever really discussed before, this idea of sequentially monitoring randomization tests, because when we think of sequential analysis, everything's done in a parametric and a population model form. So, so if the FDA were to ask one of these pharmaceutical companies to do a confirmatory analysis using a randomization test, you can now do it in the context of sequential monitored clinical trials. And I'd like to thank Rosemary and Barbara and Steve Gilmore. Thanks.
Okay, questions?
How do I get out of here? That's my question. How do I get out?
There is Henry.
Henry.
So, a traditional exact test I'm doing the same thing. You find a sufficient statistic or a suitable ancillary, and you condition on it, and the condition is that the randomization distribution under the null hypothesis should not depend on the parameters. And do you have this classical? And if you're lucky, you can do it inside the exponential family. So, do you have this classical condition? Then? As long as your parameters aren't messing around with the initial distribution, you're okay. Is that?
Not exactly, because we don't have any parameters. I've made no distributional assumptions whatsoever.
Oh, then you're absolutely fine.
Yeah.
Right.
Yeah.
But you have a notion of a null hypothesis.
I do.
Yes.
Yes.
So, but it isn't really expressed in parameters.
It's not parametrically expressed. It's are these groups equal or not, basically. Yeah.
Sorry, I'm busy
So it's
trying
not
to-
it's not a traditional non-parametric test where we assume some kind of f of x and g of x or something like that.
No, I appreciate that. Very interesting.
So this is really using the randomization, and that's it.
I mean, can I make a further remark? I mean, these big combinatorial problems which are coming along now, like comparing two genomes, where you have no distribution and you have no parameters really. You just want to get a randomization test out of this. This kind of methodology could be extremely important for really big problems, I think. So I think it's very, very interesting.
Any questions or comments? For example, Bill Simpson.
Rosemary, you don't want to say you understand me? You don't want to confirm that you understand me?
There's no possible right answer to that.
I don't see quite how this has to do with your things you do for restricted randomization.
No, it doesn't.
It doesn't.
No,
Okay,
no.
that's right.
But she's
Well, no, it's
she's
just-
a proponent of using the design in the analysis, I
Yes,
think.
that's right.
I mean,
That's
yeah,
right.
we've had some discussions about it, how if you did some of my sorts of restricted randomizations, how it would.
Oh, okay, yes, that's right. So what do you think a generalized effort rule might be? That you could do to ensure what sort of
Well, you'd have to
generalization-
calculate. Yeah, I'm thinking of your design, or
Oh, I
there's
see,
a
okay.
generalized bias coin series of generalized bias coin designs where you'd have to do a very difficult combinatorial problem to solve those
Yes,
conditional probabilities. And my student claims she can do that, but she's at a drug company now, so.
So not to be trusted, you mean?
Well, we'll see if anything's ever written up. That's what I mean. Yeah. So,
Whatever.
okay.
2/3?
Oh, yeah.
Why 2/3?
Well, Efren had in his original paper, it's kind of a in between 0 and 1. I mean, in between 1/2 and 1, right? I'm working with a student now who's doing kind of formalizing the trade-off between selection bias and variability. And we're finding that P actually needs to be further away from 2/3 in order to have a reasonable, be a reasonable compound criterion. So,
Okay, thank you very much.
thanks.
Don't walk too far away
With my microphone.
My understanding is it's 2/3 because if the die comes up with a prime, you can allocate the underrepresented treatment. But,
Well, he also we talked about. I guess you need a certain number of envelopes, right?
oh, well,
2/3.